Andrew Kelley used to work at OkCupid. One day, he was put in front of a big C++ code base, and rather than work on it, he decided on the far easier path of leaving the job to design and implement his own programming language from scratch, surviving on donations. The talk is titled Zig Compiler Internals. Andrew, the stream is yours.
Ooh, sorry, I just wasn't expecting the joke to be that good. Hey everybody, welcome to Zig Showtime. Thank you, Lourdes, for hosting. You're doing an amazing job as usual. And thank you also to Benjamin. That was an excellent talk. I love how Benjamin is always like, well, I don't know anything about allocators, and then just comes out with this content. Oh man. Okay, so here we are. We're going to talk about Zig compiler internals. Shout outs to King Prati for this picture. Let's get started. So all compilers are pretty much the same thing, and the Zig compiler is no exception. So, I mean, this is really all there is to it. The first thing you got to do, you got to take the programmer's source code, and you need to tokenize it. And this is so simple. All you do is you iterate over each character, and you figure out, is it part of a string literal? Is it part of an integer literal? Is it, like a plus sign, something like this? This is called tokenization. So this is so simple. You can do it with a regular expression, or you can write, a for loop with switch statements and sort of hand code your state machine. And what you end up with is a list of tokens. So that takes you to the next step. The next thing you got to do is take your list of tokens, and you want to parse that into an abstract syntax tree. And so this is the part where you say, okay, I see a bunch of tokens here. Is that an if statement, or is that a function call? Or, is that a function declaration, or is it a parameter? So you've got to take your tokens and turn it into the actual understanding of the language. There's a lot of tools to do this. Tools like Flex and Bison are called a parser generator, and this will do the tokenization and parsing for you, and you can sort of just declaratively describe your syntax, and they'll automatically generate the code for you. Or you can write a recursive descent compiler yourself that can help you do error recovery better. It can help you give better error messages. Or if you're an absolute madman like Kamari Spaghetti, you can write a handwritten, non-recursive stack-based parser. And if you want to hear more about that story, ask me in the QA. It's a pretty funny story. Okay, so the end of this part of the pipeline, we're going to have a tree of AST nodes. And we need to take that, and we're going to generate some sort of intermediate representation. And this looks slightly different in different languages, but it's all the same concept. In Java and C Python, we have bytecode that is this part of the pipeline. In the Clang C compiler, this is LLVMIR. In GCC, this is the Gimple. Every language has this. And then finally, we need to take that those sort of virtual machine IR instructions, and now we have to actually figure out, okay, what are we going to tell the CPU though? And this is the part where you actually have to care what CPU you have, because a RISC-V CPU and x86-64 CPU do not understand the same instructions encodings, and they certainly don't understand your imaginary IR instructions. So you have to give them actual concrete machine code. All right, and this is really it. But you could add a few more steps into the pipeline. So, for example, in between those two steps of the IR and machine code, we might add some optimization passes in. And in this part of the pipeline, we're going to start and end with the same thing. So we start with a bunch of IR instructions, and we're going to end with a bunch of IR instructions. But hopefully what we're going to do is we're going to change it so that those new set of IR instructions are more efficient. And maybe we're going to delete some dead code. Maybe we're going to promote some memory access to registers, that sort of thing. And then finally, once we once we are done with the optimization passes, hopefully we have better IR instructions. And then finally, what that actually produces is an object file. And then in order to run the object file, we need to link it into an executable. So there's the whole story. Now, let's talk about Zig specifically. In Zig, it's the same thing. This is the same thing that we were just looking at, but just to be more specific, the intermediate representation is broken into two parts. So the first part, when we take the AST nodes, we're actually going to generate untyped Zig IR instructions. So these instructions encode control flow, but they don't have types yet. And then we're going to do a semantic analysis pass. And this is the big part of the compiler. There's a file in the source code called ir.cpp that does this box over here, the semantic analysis pass. And it's 31,000 lines of code. And it's all just that box right there, semantic analysis pass. So that's the big one. And what this one does is it's going to take the untyped Zig IR instructions, it's going to iterate over them, and it's going to evaluate all the instructions and find out, do we know the value at compile time? Can we do the control flow at compile time? And if yes, then it does it. And if no, then it's going to emit runtime control flow and runtime instructions. And then finally, since
Sorry, Andrew.
Zig uses...
Sorry to interrupt you. I think your desktop went black.
Oh, no.
Can you double check?
Yes.
No worries. That's the beauty of having me here, so we can diagnose this stuff immediately.
Yeah. It seems to be working. Should I refresh the Laplace?
Okay. Let me then double check that it's not on my side.
Oh, I just exposed the room as well, by the way.
Don't worry, we are not seeing anything. And give me a second. So here's what I'm gonna do. I'm transitioning to a logo, so people don't see anything. Don't worry. Now let's diagnose what's happening here. Okay, I can try to refresh page. Okay, I think it's working. So you know what? Might even be my fault. I apologize for that.
Oh, no worries.
Yeah, you can.
Tell me when.
You can switch back to your view, and I'll transition back.
Okay. So everyone heard my audio, is that right?
Yeah. It's just the video that stopped.
Okay.
You can start.
Okay. Sorry for the hiccup, everybody. So anyway, we're looking at the big box on the bottom right, and we're going to take the untyped instructions. We're going to do compile time known things at right now, and then if anything that we can't do at compile time, we're going to emit new Zig IR instructions, and this time they have types. And then finally, because Zig is using LLVM, instead of Zig making machine code, we actually just change the Zig IR instructions into LLVM IR instructions, and then the Dragon takes it from there. And now what I've just described here is stage one. So I put the familiar GitHub label on the top right there. You've probably seen that on issues. And if whenever you see that label, you're probably also used to seeing this label next to it. So I'll just put that up right there too. That's just a joke. Anyway, that's the process for stage one. And I know that it's not always, if you're in the IRC channel or the Discord or whatever, we're throwing around these words: stage one, stage 0, stage 2, all these things. So I want to tell you what's going on with that. So that's how the compiler works from a code perspective. Here's how we build it. And like, what are the stages? So the first thing that we're going to do here is we're going to take all this C++ code, and the C++ code implements Zig, right? Because before we have Zig, we can't write Zig in Zig. And what we do is we compile all of this C++ code into a static library called libzigcompiler.a, and we then also throw in one more C++ file into that, and that's going to create Zig 0. So that's actually stage 0, not stage 1. So once we have that, we have a Zig compiler. We can compile Zig, but it's missing a lot of features. All the things we're used to having: Zig format, Zig CC, translate C, all these things. You can't do them with zig0.exe, and that's because that stage2.cpp file, it's a shim. It just contains a bunch of code that says, oh, if you try to do Zig format, crash, panic. If you try to do translate C, crash. I don't know how to do that. I'm just a shim. All these things with the red X's will just crash if you try to do it with zig0.exe. But it can compile Zig code as long as you don't use these features. So what we do is we take zig0.exe and we then use that to compile some code from the self-hosted compiler. And the sort of main file that is here is the stage2.zig file. And now look at what we're doing here. We're taking the same libzigcompiler.a, except instead of stage2.cpp, we're using stage2.zig. And we combine these together, we link these together into zig.exe. And that becomes stage 1. And now we have all these features that we didn't have before. So now we can do Zig format, we can do translate C, Zig CC, all these things. So that's how you get from stage 0 to stage 1. And the beauty of this is that all that .zig code, that is code from the self-hosted compiler. So we're actually sharing code from self-hosted compiler, even though it's not, even though we're not fully self-hosted yet. Okay, so what do we do next? What's stage 2? Well, I just moved everything over to the top left here. So once we have stage 1, now we're going to take all of the Zig self-hosted compiler code. You can see some of these files are the same, but there's also more there. And now we don't need the glue code of stage2.zig anymore. That was just the glue code to put it into the other compiler library. So now we're going to actually compile all the stage 2 code, and finally we end up with the self-hosted compiler. And that's where, and you can do this right now, but it's not done yet. Like you've probably seen some of my demos where it can compile like some hello world stuff, but it's not ready to go. We can't ship it yet. So actually we're still shipping stage 1. If you go to ziglang.org/download, this is what you're getting stage 1. All right. So hopefully that gives you an idea of the build process and how this stuff works. Now this is the part where I'm going to show you a demo. So let's go over the same sort of pipeline in stage 1, and I'm just going to give you like a tour of the code. So if you're curious or you want to contribute or you just want to like kind of like know your way around stage 1, now this is where I'm going to show you where everything is. Okay, so the first thing we do is tokenize, and now I'm going to tab over to my Vim here. So the tokenization code in stage 1, it's in this tokenizer file here. And let's look at the data structures as well. So all we're going to do here is turn source code into a list of tokens. So the main thing here is this enum, and you can see the enum has everything like a bang, or has all the keywords in it, and it has like a string literal. So that's all the different tokens, and there is some a little bit of extra code here for special stuff. It's also using a lot of memory per token, which could probably be improved. But anyway, point being, the thing we're going to end up with is this list of tokens. So in order to do this, this is a hand-coded tokenizer. Got to list our keywords here, and we have essentially a state machine. So this is an enum of states. and then the main tokenized loop is going to look it's going to look like a very certain pattern. So here it is, the main tokenized loop. We loop over the source code, switch on the state, switch on the character, and then we either emit a token or switch states, and that's it. That's the whole thing that a tokenizer does. So I'm going to sort of scroll through here, and you can just sort of see the structure is really consistent, right? Switch on the state, switch on the character, emit a token, or switch states. That's really all there is to it. It's really easy to debug. It's easy to add stuff to, and we end up with a list of tokens. So that's it. That's the tokenizer. Next, now we have a list of tokens, and we need to create a tree of nodes. We need to actually understand the syntax. So that's going to be in the parser code here. And the type that we're going to end up with is this AST node struct. Now, again here, I'm using a union for all the different types of AST nodes, which again is pretty wasteful of memory. That could be improved. But I mean, it gets the job done. So what we need to do is create these nodes, and each one of these nodes might link to other nodes. It's a tree structure. So that's what we need to end up with. And so what this is going to look like is this is a hand-coded recursive descent parser. There it is. And so what it's going to look like is we have a bunch of functions, and we're going to, it looks a lot like the grammar definition. So here we're calling parse container members, and you can see that the functions sort of have this text in front of them that gives you an idea of what it's supposed to do. So we're looking for a test decal, or we're looking for this, or we're looking for this, or this, or this. And so you can see we try looking for a test declaration, we try looking for a top level comp time, we try looking for a top level declaration, and at the end, what we're going to do here is we're going to emit an AST node. So you can find, I think it's like AST create node. Yeah, this function is going to be called everywhere here. We're just creating these nodes, we're hooking them up, we're returning them, we end up with a tree. So next, we need to take these AST nodes and we need to generate our untyped Zig IR instructions. Okay, so the types for this is here. It's IR, it's circ. There it is. So this is sort of like the base struct for this thing that we're going to generate here. Now, let's go look at this enum here. So these are the types of untyped IR instructions that we can emit. So you can see there's declaring a variable, there's a branch, conditional branch, switch branch, there's a binary operator, a unary operator, you can load a pointer, unreachables here. So this is where we flatten out the AST into a set of instructions. And what this flattening can do is it can turn, for example, a while loop and a for loop into basically the same structure, so that you don't have to code you don't have to write the compiler code for a while loop and a for loop twice, because these can just emit instructions, and then you know how to operate on the instructions. So where this happens is in this function called, it's in ir.cpp, this monster file that it has 32,000 lines in it. I think it's AST gen node raw. There it is. Okay, so this is sort of like the main function here, and you can see that we're switching on the AST node type. So if we see a block, we call this function. If we see, a binary operator, if we see a string literal, that sort of thing. So let's look at a really simple one. Let's look at a string literal or integer literal. There. So we're looking at this part here for an integer literal. So here we have a node that is an integer literal. It's super simple. We don't have to do any logic. All we do is we create an instruction which is a constant, and the AST node has the big int value of the integer literal, and now we just have a constant instruction which represents this value. That's the simplest possible one. Now let's look at a slightly more complicated one. So we're going to look at I think let's look at a unary operator. Which one am I looking for here? Anyway, let's look at a binary operator because I didn't find the one I was looking for. So we have assignment operators. Let's look for like add. Okay, so here's one. So here, yeah, this is a good example. So here we're doing a binary operator. And you can see we're recursively calling IR generate node. And so again, this is the part where it's turning AST nodes into instructions. So we get an instruction for the left-hand side of like the add, for example. We get an instruction for the right-hand side of the add, and then we emit a binary operator with these two instructions. So pretty simple. So once we're done with that, this is where all the magic happens. So now we have a set of untyped Zig IR instructions, and we need to do comp time evaluation, comp time control flow, and then emit runtime instructions. So all of this happens in this function called IR analyze. And there's there's a bunch of debug stuff here, but the main loop is here where we're iterating over the old IR instructions. And the main thing here is right here. So here we're passing in the untyped Zig IR instruction. We're calling IR analyze instruction. We're getting the new instruction. This is the single line right here. It represents this transition right here. And so if I go into this function, again, you can see we're switching on the type of the untyped instruction, and now we're doing the analysis. So I think the one I wanted to show you was bool not. Yeah. So let's look at the analysis for Boolean not here. So this is what this part looks like for a Boolean not operation. So the first thing we're going to do is just get the operand. We're going to get a handle to the Boolean type. Then we're going to cast the operand to the Boolean type. And this code right here is the part that will give you a compile error if you tried to do a Boolean not operation on, like an integer or a string literal or something. This is the part where it would tell you like expected Boolean, but found something else. If you delete this code, then you'll get a compiler crash instead of a compile error. And then finally, this is the part where we're doing compile time stuff. So this pattern is good. This is a representative pattern of how this works in all of the compiler. So all we're going to do is we're going to check if the operand is compile time known. If it is, we get the value, the compile time known value. And in this case, we're going to emit a constant.
Andrew, sorry to stop you again.
Mm-hmm.
I think the video broke down pretty bad in the last like 30 seconds or something.
Okay.
So I think people were stuck seeing the bool type example.
Okay.
Can we try to redo the? Can you try to share me another link?
Yes.
Sorry, there have been a couple of hiccups also during the presentation, but I've been restarting the stream like very fast, so I didn't want to interrupt you. But I think that we're probably far apart. So for the people watching, Andrew is closer to the West Coast in the United States. I'm in Europe, so it hasn't been a problem up until this day, but that's what you get when your whole network is best effort.
Let me know if we're good. I sent you a new link on Discord.
Let's see. Yeah, it's loading really, really slowly. So, what if you try to enable screen sharing on Discord? I think we
Okay,
can make
I will
this
do that.
work.
Yep, on it. Okay. Wait, why does it say go live?
That also works, but you have a share your screen button. You should have it on the right side next to the video button.
Okay, I click it.
Sorry, everyone. We're going off stream with the audio for a moment so that we can fix this. Be right back. Okay, I think we can resume.
Okay, am I live?
Yeah, you're live.
Okay, great. Thanks everyone for your patience. Don't worry, I anticipated this, and I put a little picture in the bottom left here for you, so you can see what I look like. Right, so we're in the middle of talking about this part of the pipeline, and I'm showing you what a Boolean not looks like, right? So if you do the bang on a like a true or a false. Okay, so we went over that this is a part where it does type coercion. So this is a part where it gives you compile error if you try to do a not on a non-Boolean. Finally, this is the heart of how comp time works. So it's actually pretty straightforward if you think about it. So we check the value. If we know the value at compile time, we know that it's true or false at compile time, then we just get the value. And we just do the Boolean not right now. So right here, there you can see we're doing it. And we just emit a constant instruction rather than adding the instruction to the list. Now, if that doesn't happen, if we don't have the operand as a comp time known value, then we go on to this part. And this is where we actually emit a runtime instruction for the next part of the pipeline. Right here, we're adding the emitting a runtime instruction. So that's it. That's how this part works. And what we end up with is now all of the stuff that could be figured out at compile time is done. It's gone. And the stuff that's left over, the stuff that we only know at runtime, makes it to the next stage. So now we're on to this part where we render the typed Zig IR instructions into LVM IR instructions. Now that happens over here at CodeGen. And this function's kind of long. We got to do a bunch of stuff, but basically at the end here, we're going to be calling IR render. So this is the part where we're doing this for each function. So now we're going to iterate over the Zig IR instructions. Sometimes we can skip them. But again, we have this one line here, which is sort of the heart of the issue. This one line represents this just transition here. So here, again, we're having a switch on the Zig IR instruction type, and we're going to do something different depending on which one it is. And so let's go find our example again, our bool not. So in the case that we had to emit a runtime instruction, we can see what we're doing here. Where actually LLVM doesn't have a Boolean not, but it has integer comparisons. And the way that we represent Booleans to LLVM is with an I1. So this value is going to be an I1 because it's a Boolean. And then what we do is we take the value 0 and we say if the operand equals 0, that's our result, right? Because 0 equals 0 will turn into 1, and 0 equals 1 will turn into 0. So it flips the Boolean around. So there we go. And now we have an LLVM IR instruction. We can look at one more interesting example here, unreachable. So if we emit a Zig IR instruction for unreachable, then we're actually going to check, do we want safety on? In this case, we're actually going to emit a crash. Otherwise, we're going to actually emit a LLVM unreachable instruction. So finally, we've given LLVM everything it needs. LLVM takes it from there. It does all the stuff in the back end. And what this is going to leave us with is an object file. So that's gets target machine emit to file. There it is. So this is going to end us with an object file. We're not quite done yet. We have one more thing to do. We need to turn the object file into an executable. And so finally, we have to, depending on the kind of object file, is it a Windows one? Is it an ELF one? Is it the Mac OS one? Or is it a WebAssembly one? We have to basically construct a linker line that we're going to send to, again, LLD, another part of the LLVM project, that will then do our linking for us. And then once this is complete, we have an executable, we can run it. All right, that's it. Now, there's a lot more details here to go into, of course. We might want to talk about self-hosted, stage 2 and how that works and how it's different. It's designed fundamentally differently. We could talk about the cache system, debugging tips. If you have any requests, let me know. I can fill in. I could do more on this sort of like series, if we need to fill in more slots for Showtime. So, however we want to do that, we can do that. And that's it. With that in mind, I think it's time for Q&A.
Yep, thank you. I didn't notice I was muted. So let's switch to the Q&A. Thank you very much, Andrew. Sorry everyone for the screen sharing issues. I think Laplace has never let us down before. And I don't know, I think we're gonna diagnose this. We did try briefly to make sure it worked, but who knows? Maybe we'll find a solution. But certainly we'll figure it out, an easier, more accessible fallback option in case this happens again. So Andrew, while people start thinking about questions, I think I'm contractually obligated to ask you the first question. I'm sorry. When did you discover Zig, and how did you discover it?
I discovered it in the shower. Yeah. No, actually, I actually could tell you a little story about that. I was working on a digital audio workstation as sort of my big project, and until that point, I'd always just bounced around on little projects, and I was interested in so many things, but I couldn't stick to one project. And so my goal was to pick something really hard, like a digital audio workstation, and just focus on it and actually put a lot of time into it and make it into a big project that it's, worthwhile and actually, accumulates, some critical mass and that sort of thing. And I was doing pretty good on that, but I actually like went through like a breakup at the time that was kind of hard, and I thought, oh, I need to just like relax and have some fun. So I started working on a programming language instead of the thing I was supposed to be working on. And oh man, a programming language is so much easier than a digital audio workstation. It was just such a joy, you know. Uh, so that's how it started, and then I just didn't stop.
I see. So, so you're basically, this is a big parenthesis, but you know that once you're done with the language, you will have to go back to that then.
Yep.
I see. I see. So, I have another question for you. So you mentioned that all languages go from an AST to IR, and then to machine code. So, what prevents compilers from going directly from AST to machine code? What does the ER provide in the middle?
That's a good question. So nothing really. Like you could do it, but you'll find yourself duplicating a lot of things. So as an example, if you have a while loop and a for loop, and other languages have a lot more syntax, so maybe they have 2, 3, 4, 5 different ways of looping. If you do it with an AST, you're going to find yourself writing code that's very repetitive and like duplicated for each of these different constructs, and in a way that's very hard to abstract. It's very hard to like dry up your code, and also, so if you do the IR, then you end up having all of those syntactical constructs take the same path, which is easier to maintain. Finally, if you want to do any kind of optimization, um, doing optimization on an AST is a nightmare. It's just, I mean, it's I think that's what they have programmers doing in hell, is trying to do optimizations based on an AST rather than like a intermediate representation. I don't even know how to explain how much of a pain it is. I think I think in my college course we tried to do optimizations on an AST, and it's just not feasible.
I see. Okay, I see there are some questions piling up. Second question, in case somebody else wants to add a question. So I remember watching a while ago a video by Rob Pike, who was on stage and was presenting a detail about the Go compiler, where he was making a great point of the fact that the Go compiler had a intermediate stage before generating machine-specific code that was shared by all, let's say, architecture-specific backends. Did you watch that video?
Yeah, I'm familiar with that. That's specifically for the Go assembly language abstraction layer. Is that right?
Yeah, I think so. So how does that relate to what you showed us?
How does it relate? Oh, okay. So in the pipeline, that would be.
I can put your screen back on the
No,
screen.
don't worry about that.
Okay.
It doesn't actually go. Uh, Wait, I'm trying to remember. Is that part of their code generation, or is that just part of their assembly pipeline? Yes,
I'm not
it's
sure
part of
if I
their
remember.
code generation. So actually, yeah, can you put my screen back on?
Sure. I think you need to share it again, though.
Oh, right, of course. Thank you for reminding me. Oops. Okay, are we looking at my screen?
No. Give me a second. I don't see your screen share. I think I. Can you try again?
Yeah.
I mean, I can see myself without the webcam. Okay, now it works.
That works.
Yeah.
Okay. Right. So this is the whole pipeline here, and the way that Go has their setup, they have an additional box right here in between render IR instructions and the machine code instructions, and yeah, this box here is split into two. So what they're going to do is they are going to have this step, but instead of rendering IR instructions directly into machine code instructions, they have another layer where they render it into like a second IR layer that is basically just machine code abstracted across architectures. So that's how they do it.
I see. Because
There's
because the IR is designed by you, right? Your IR is whatever you want it to be, right? While these assembly, the Go assembly is much more closer to what the general parts of that all architectures share.
Yeah, that's right. So what Go has done is created a virtual machine that very closely resembles a virtual machine that's designed to be as close to all of the actual machines as possible, yet still abstracting across them. And so then they target that layer, and then what that does is it just makes it very easy to add another actual machine that comes out of that layer.
Right. Do you see this being something useful for the project, in your opinion? Something that you would want to investigate in the future?
I actually put a little bit of thought into this, and after I watched that video, I think that there is a specific reason that Zig's design goals are different than Go's. That means that we should not do that. I think that if your goal is to support only the most popular architectures in the world, then Go's approach makes sense. If you only want to do x86, ARM, whatever ends up being popular. However, one of Zig's goals is to support even exotic architectures, like a truly general purpose language that can support weird architectures. And in this case, you can see how the abstraction across weird architectures would not quite fit. And in this case, we would need inline assembly that is more specific to exotic architectures. So we have less to gain from this kind of abstraction. So for that reason, I think that this would not be an appropriate layer to add to Zig's compiler design.
I see. Thank you very much for that answer. So let's do a few questions from the audience. First question from Timmy. Did you write any compilers, maybe toy compilers, before Zig? And or what was your first experience writing a compiler?
Yeah, I did one in college. The problem was to create a Pascal sort of language, and the professor wanted us to compile it into C, but that just felt such like cheating to me. So we got the professor to agree to make it so that we had to emit MIPS instead of C, and that was a lot more fun. That was my first compiler project, but here's my actual secret. I said we because I did the project with my good friend and roommate from college. His name is Josh. And Josh has written a lot of compilers, and he was very involved in the early design decisions of Zig, and still involved today. I still call him up on the phone and talk over a lot of the issues with him. So that's my real secret. I just have a friend who's really good at this stuff, and then just will talk to me on the phone about it.
I like this strategy, by the way. Yeah, having other people do stuff for you, it's amazing. Yeah. Another question from Suirad. Are you excited to rewrite everything in Zig?
Oh, super excited. I've started. You can check out what we have so far in self-hosted, and it's it's so nice. I mean, it's a nice piece of software. It's already extremely fast. I mean, it doesn't support a lot of the language because it's not done yet. But the thing is, like, if we can just like if it just keeps the speed it's at now, it's going to be incredible. Like, all we have to do is not slow it down from what it's already at. Like, if we could just add more of the language without making it worse, it's going to be great. And I mean, like, the incremental compilation is working. Like, the design is good. The way that it emits machine code instructions is working fine. Like, we're even set up. Like, I didn't realize this at the time, but with the way that incremental compilation is set up, it's actually just not that much more work to add hot code swapping. Like, actually, like, really robust hot code swapping. So yeah, I mean, it's great. The like coding in Zig is great. It's a good language, and so the project is really exciting. My only sadness is that I just can't go any faster. I'm just doing a lot of the hard design decisions up front at the beginning, and progress just feels really slow. But I'm convinced that it will pay off to invest in these difficult design decisions up front.
Another question. This is from Luna. What about the non-recursive stack-based parser that you mentioned earlier?
Nice. Yes. So if you've been following along with the recursion story in Zig, then you will know that we now have a plan so that, like a recursion plan where you can't just do naive recursion. You're going to have to sort of like do some stuff to heap allocate the recursive frames. Or anyway, point is, you're not going to be able to do like normal recursion, but we have a plan so that you can express your code just recursively still. That didn't used to be the case. It actually used to be the case that we just thought we weren't going to be allowed to use recursion in Zig at all. So as sort of a proof of concept, I sort of started doing the self-hosted parser in without using recursion at all, right? Like, I'm talking about writing a recursive descent parser without recursion, using like a stack and just creating all these like structs and stuff. And I just like did a little bit of work on it, and I was like, okay, I think this might work. And then I just went on to like work on other stuff. And then Komari came along and finished it, like just did all the work and wrote the whole self-hosted compiler with no recursion. And two things. One, quite frankly, it was just like a difficult code base to maintain. Like, recursion is useful. It's a nice way to express recursive concepts. So it was kind of annoying to maintain the code because you had to like think about it in a really weird like stack-based way with like structs and types and all these things. It was almost like a whole like language you had to learn to write the parser. Okay, but two, the fact that Jimmy did that, Komari did that, was incredible. Like, so much respect for pulling that off. And it was almost sad when we had to, retire the code and favor the more maintainable recursive version. And that work was done by Stevie Hershew. But don't worry, because we have the pull request where it happened, and there's a lot of like rose emojis and like gravestone emojis and stuff. So, there's a nice little like grave site for the old code.
So you gave it proper burial.
Yeah, proper burial. Yeah.
I see. Okay, let's see other questions. What part of the compiler must give you headaches?
Yes. That could be an entire future topic, and it's the part where result location semantics, compile time semantics, inferred variable types, and inferred peer type resolution and inferred comp time all in the same expression. That code just doesn't really work, and you're going to hit compiler bugs, and it's not really fixable. The design of stage 1 is not really at a place where that can be solved. It's just a disaster. If all those 5 things combine at the same time, there's no plan for that in stage 1. It just doesn't work.
You need a better language to handle the stuff, right?
Yeah, exactly.
So how did you check the Zig grammar? Timmy says, I often find myself struggling to fully understand and or eliminate left recursion, etc. Do you actually remember all the theory from uni?
Oh no, I don't remember any of that stuff. I just had a lot of help from the community. So Kamari actually wrote a. Someone could probably drop a link in the Twitch, but there's a Zig spec repo, and it has a parser expression generator definition for the Zig language, and so you can use that to you can use that as a formal specification. Kamari just did that, so that's really helpful. Earlier on, when I was doing a lot of syntax stuff, I would call up my buddy Josh, or we were roommates actually, so I would just go into the living room and I would say, hey, I need to change the syntax of Zig, and here's my idea. And he'd be like, no, you can't do that. I'm like, why not? And he would explain like all these things. And then I would say, oh, okay, well, what about this? And he'd be like, no, you can't do that either. And like, finally, we would just get to a point where he goes, yeah, that'll work. You could do that. And I was like, okay, thanks. Honestly, that's how the syntax evolved of Zig.
So Benjamin asks, why did Zig use the percentage operator, and why was it removed?
Yeah. Why did I do that? Yeah, I don't know. I think earlier on I was there's sort of two things you have to work on at the same time. You have to work on the syntax, which is like the clothes that you're wearing, and you have to work on the semantics, which is like what does the robot body look like? You know, that's a weird analogy. Anyway, point is there are two sort of like completely orthogonal problems where like one is how something looks and the other is how it functions. And I mean, you can just work on these problems independently. And so for a lot of situations, like it's easier to just focus on one and worry about the other one later. So double percent was a good example of that, where I just needed some syntax so that I could test out these semantics I wanted to test out. And I don't know, I didn't really want to get locked into or like, I didn't have the brain power to solve two of these different problems at the same time. So I figured out how the semantics should work and I felt good about it. And then later I realized that the parentheses were just too ugly for people to even like pay attention to the language at all. And so keywords, and also we made it so that all control flow happens exclusively via keywords, and that was a good decision. And in retrospect, like I'm also happier with the way that the syntax evolved. So I don't know. To summarize, earlier on I focused a lot on semantics, and then for me, like the syntactic choices just take a lot of like time to sleep on it and just get some input from a lot of different people, and then finally you pick something that hopefully doesn't have to change.
You also answered, I guess, partially the next question. So I'm gonna ask you the second half, which you didn't address specifically. So, is maintaining a syntax close to C, C++ an important design choice for Zig?
I'm not sure it's explicitly the reasoning behind it. I guess what the alternatives are would be like a Lisp sort of syntax, or I don't know, a more exotic one. I do think that there's a lot of value in having people who know programming languages but not the Zig programming language be able to look at Zig code and already be able to read it without looking up any documentation. I actually think that that's a big deal. Like I think that I think the film familiarity does matter, but ultimately, I just want syntax that's easy for humans and easy for computers to parse both. That's the main sort of actual drive.
So let's shoot questions. Let me do the second one first, then I'll finish with the other one, Timmy. So I'm not skipping one. I'm coming back to that later. So how did you get started with the LLVM part? The documentation seems extremely terrible. Did you power through, check the toy language example in the site? Do you have prior experience? How did you feel about that bit?
Yeah, that's It's a good question. So the documentation for the LLVM IR is actually pretty good. There's like a langref.html file, and it's quite extensive. It explains all the instructions, all that stuff. It's pretty good. As for the actual API, yeah, you basically have to read the source code in order to use it. But yeah, I mean, I think that I was just so fascinated by this how powerful this API was, especially before I got into doing any compilers, that it was just it was interesting enough, that it made me want to play with it. I did the project. If anyone remembers, like a few years ago, I think I called it Jamulator, statically recompiling NES ROMs into native executables. That was sort of my like first foray into using LLVM and Clang and stuff, and I had a fun time with it. So from that point, I realized that was sort of a library that I could use for code gen if I wanted to.
Okay, final question from Twitch chat. Still from Timmy. I recall a plan for a non-LLVM backend for Zig. Does that mean that Zig would generate assembly for all supported targets?
Yes, not assembly though, machine code. Assembly would be the human readable version of machine code, but we don't even have to do that. We can just skip that step straight to machine code. And in fact, that is what the self-hosted compiler right now, as it stands, does not have an LLVM backend. It is only a purely self-hosted backend. And the plan is to make LLVM an optional dependency. Right now, it's not even a dependency at all. So when you use a self-hosted compiler, Zig takes your Zig code, does some analysis, and then it's going directly into the binary file. That's why it's so fast. So the plan, the grand plan for the future is that LLVM gets tacked on as an optional dependency, and so there will be a fast debug backend. The point is just we want to compile fast, and then when you want to go into release mode, that's when the optional LLVM dependency would be useful, because now you go through LLVM, you get all those optimizations. You're willing to wait the extra time for that release build, and then we have the best of both worlds. But yes, the answer is yes. It does depend on writing architecture-specific code for every architecture that you want to support.
Okay, awesome. So I guess we can conclude with one final question from me, which it's not really a question actually, but I think I think this is a good opportunity to inform everybody of what's going on. So why don't you tell something about the next Showtime episode? Why are there no speakers?
Yes. Okay, so next week, no Showtime. Next week after that is going to be a special episode, and we're going to have some long-awaited announcements regarding the Zig Software Foundation, and I think it'll be worth attending.
Whoa!
That's all I got.
Yeah. So yeah, it's gonna be interesting. It's gonna be more interactive than usual. We also made sure for once to give something back to the poor people in Australia, so that they can also join one episode, which I think is going to be probably the most important one up until today, so that they don't feel excluded, even though I do still think that they should apply to speak. That's the right way to get Showtime in your time zone.
That's a good point.
Yeah, but it's gonna be awesome. If you can be there, you want to be there, I assure you. That said, we still have a lot of work to do for that episode to happen. So that's why it's gonna be 2 weeks. Well, thank you very much, Andrew. Is there anything else that you want to say before we close?
Take care, everybody.
Awesome. So let's switch directly to the end scene from here.